Hey everyone. I wanted to pick a challenging kind of calorimeter question, and this is probably one of the most complicated ones that I can envision being on your quiz. Um, and so I've done some things, sort of prelim here, to get us to think about it the way that we should. Okay, so this is a crude illustration of a calorimeter. Um, a lot of times these are used to verify the specific heat of materials that are already known and just see how close you are to a known value. So they can be used a lot of times to verify the authenticity of substances. Uh, you're never going to have to remember all these equations and relationships. I'm always going to provide these. I just forgot to put them on this one. Um, and so we want to think about the calorimeter in this way. You're measuring the temperature of the water, which in this case is the surroundings, not necessarily the system. Okay, so I'm just going to read this to you, and we're going to write down everything we know about the water, and then whatever object seems to be in the calorimeter. In this case, I said aluminum, but it could be any kind of thing. 250 mil calorimeter. Okay, stop right there. Anytime you see distilled water, we're going to assume the density is 1 gram per mil. So I know that the mass of the water is just going to be identical to the milliliter value there. Okay, so that's my first thing. Okay, just make that mass. All right, here we got an initial temperature, blah, blah, blah. We add some aluminum. After 5 minutes, they come into thermal equilibrium. Now, what's important here is that no matter what, heat, we'll say Q, or energy, will flow spontaneously, which means without any effort from anything external, from an object of higher temperature to an object of lower temperature. So the directional flow of that heat is going to be important. And so, okay, thermal equilibrium is reached, and then we have a lower temperature actually than when we started. Okay, now here's something that's important. Because the water was at a temperature that was higher than where it ended, it must mean that the aluminum was doing the absorption of the heat because the water was at a higher temperature. And how do I know that? Well, one, I wrote the question, but two, I can see that if I take the change in temperature, which is my final, minus my initial, I'm going to get a negative number. And so it's important to know that heat, in this case from the water, isn't being released, it's not being absorbed, it's being released. So I should get a negative Q value here. And let's see if we do. Because if I take 18.6 and I subtract it from 25, I should get negative 6.4. And so that's going to be my change in temperature for my water. Lovely. I'm always given the specific heat of distilled water at 4.186 joules per gram times Celsius, not Kelvin. I guess you could use Kelvin. Anyway, so I know everything about water enough to get the Q value, or the heat that was either released or absorbed. And like I said before, I know it's going to be released here because if I have a negative delta T, that substance is donating heat into an object of lower temperature. So if I take the Q value of water, I say Q equals mc delta T, I just put in what I know, 250 grams because it was distilled water, multiplied by my specific heat of water here, which is 4.186. Finally multiplied by my delta T, which is negative 6.4. I'm going to get a number here. And that's going to be heat released by the water. Again, proven by the fact that my change in temp had to be negative. This is taking me a little longer because I have to use a stupid calculator on my computer. It's very sluggish. Okay, so I get, this is what my calculator is going to show, 6,697.6. I need to show that with 2 sig figs. In this case, it's going to be pretty easy. I could just do 6700, and that would be joules. It will be a negative value, indicating released. So now I can use that to find out more information about my metal. If we think about our metal, we don't know the mass of the metal, and that's what we're being asked to find. I should have said this. The specific heat of aluminum is actually 0.90 joules per gram C. You'll need that. Aluminum has a very high specific heat for metals, which we won't talk about this year, possibly ever with some of you. Anyway, so I know my specific heat. I do know my change in temperature, and it actually is implied here, because when they both sit and reach a thermal equilibrium, this is going to be my final temperature of the aluminum, and this is going to be my initial temperature of the aluminum, which is at -5. And so, if I think about my change in temperature, I've got my final, which is 18.6, minus my initial, which is the same thing as like adding 5. And that's because it's already at a negative. So I've got 18.6. Oh, come on. My change in temperature is going to actually be 23.6 degrees. And I know that my specific heat of aluminum is 0.90. Okay. When I think about the metal, I think the same thing, Q equals mc delta T. I don't have Q and I don't have M, but I actually do have Q, because the negative Q released is equal to the Q absorbed. So, based on this relationship, since the water was doing the releasing, I have a negative 6700 joules is going to be equal to my Q absorbed. Since the aluminum was initially at a lower temperature, heat will spontaneously flow from high to low, so the heat or energy was going into the aluminum. And so I'm going to know that my Q is really a positive 6700 joules. And so now that I have my Q value, I can easily find M. Now, let me zoom in here a little bit. Oh, very nice. You could put the numbers in, that's fine. I'm not going to stop you. I just caution against it from the standpoint of you're going to carry a variable with a number. It starts to look a little busy. And so if I want to get M, let's just do it an easy way by isolating it algebraically. I know it looks weird, but you know what? It'll get us there in one step. And so I have Q over C delta T equals mass. And so then I just put in what I know to be true from what I wrote over here into this very simple equation. So I'm going to get 6700 joules. Okay, times 0.9, which is going to be my specific heat of the metal, divided by my delta T, which is going to be 23.6. I wrote a lot of units here because you'll see that joules will cancel, and this is like 1 over C times C means I have no C anymore, and so I just have 1 over grams, which is the same thing as grams, which is our unit of measure for mass. And so this will also prove to me that I have done it the correct way. Okay, so I have 6700. Calculator is going to output a value of 315.44425, whatever. Okay, too many sig figs. I need to show 2 here. Let's just go with 320 grams, and that's how you do it. This will probably be the most advanced kind of question you could face, where there's some algebraic rearrangement, there's some interpretation here with this Q released equals Q absorbed. Having to know the relationship between heat and how it flows. So hopefully that was helpful. If you missed some time, maybe this will help you as well. Um, I would say try to, if you don't draw a picture of a calorimeter, try to envision what's happening in your mind so that you know what substance begins at a higher temperature and where is the heat going, which substance is going to be releasing, which one's going to be absorbing. Write down everything you know to the left margin. It just makes it easier to insert later, and it kind of gets you started a little bit faster. So hopefully that's helpful, and I'll see you when I see you.